All right, let's get started. So it's five sharp almost. All right, so welcome everybody to this webinar into deep learning for image data without code. My name is Roberto. I am a data scientist on the evangelism team at KNIME. And today, together with me, there is also Emilio, who is willing to and ready to answer your question in the Q&A part. Thank you, Emilio. All right, so let's have before we start, so we start slowly, so maybe in the meantime, there's more people joining us. Before we start, let's have a look at the agenda for today. And here it is. Right, so we have a 45 minutes webinar that is starting right now, which is followed by 15 minutes Q&A session where you can ask your question. You can also unmute yourself at that point, but for now, please unmute yourself so you don't, you make sure not to disturb others. You have the chance to ask questions during the presentation in the Q&A section. And as I said, Emilio, a colleague of mine, will be there to answer your questions. The session is recorded and will be made available on YouTube next following days. And also the slide will be made available on the KNIME forum, and example workflows are already available on the KNIME Hub. So you have all the material to try it out at home or to rewatch the presentation on the webinar. So the agenda for today, that's how it looks like. So we're gonna start with introduction to computer vision, just what it is and why it matters. And then we move to the next important point, and how does a machine see images? And there we need to stress the importance of a numerical representation of images. The next, let's say, subchapter entails the challenges of working with image data. So, and how can we do that? How can we, let's say, overcome those challenges by using, for example, filters to check for different features? The almost last section has to do with convolutional neural networks. There we're going to introduce a structure that is usually made of convolutional layers, some pooling layers, and a fully connected feed-forward neural network. And then finally, we're going to have a look at a few applications in computer vision with KNIME, specifically image classification with a simple convolutional neural network. And then we're going to repeat the same task, but this time using transfer learning, in particular the VGG16. Before we dive into the presentation, to the webinar today, I would like to give you, let's say, very few hints about how you can do deep learning in KNIME. So how can we do that? Is it possible? Yes, of course. And that's how, let's say, the structure looks like. So we have on top of it, we have the KNIME graphical user interface that makes, obviously, the working with deep learning a much more enjoyable and easier experience. But the graphical user interface builds on, let's say, on a set of libraries in the background, specifically the Keras libraries, which are built on top of TensorFlow. And both of them can be accessed via Python. And so basically this combination, this pyramid make it possible for you to use in a very nice and codeless way these libraries and build and define your deep learning neural networks. How can we operationalize, let's say, the installation of this? First of all, of course, you need to download KNIME Analytics platform. And then what you need to do is you need to have an Anaconda with Python 3 installed in your local machine. And finally, we have two integrations. So KNIME Deep Learning Keras integration and a TensorFlow integration that you are required to install. And when you will have the slide, there is a link there to the documentation where it's explain in details how you can set up your KNIME Analytics platform for deep learning. All right, enough with let's say installation hints. Let's dive into computer vision. And so, what is computer vision? So there are a few definitions, and we're gonna quote Wikipedia on this. And computer vision in general deals with how computer basically can gain high understanding, a high level understanding out of images and videos. And One of the main reasons why we need computer vision is because we try to understand and automate a task that would otherwise be carried out by humans. And that's, of course, imagine when we have hundreds and thousands of images, having a human looking at all of them, it's a rather expensive and time-consuming task. So we want to automate that process. And how we can do that, we can use, of course, computers. And computer vision, in that sense, is concerned with the automatic extractions of those important information and features out of images or a sequence of images. So as I was already mentioning a few seconds before, the reason why we need computer vision is simply because there is just too much data out there. There is an increasing amount of video and image data being produced. As a reference, imagine that there are, every minute, there are 30,000 minutes of video being uploaded on YouTube. So imagine how hard it would be and how expensive it would be for a human to go through all of that and perform some tasks. So we need some automation there. And computer vision can cover many different application areas and use cases. Here you see we have a few ones, for example, image classification or image recognition, such, for example, the detection of diseases or anomalies in machinery, for example, or face recognition, or as you can see in the slide here, object recognition. That's to say, basically, using a frame around object that identifies which object is there. But we can also use, let's say, computer vision for more creative tasks, such as, for example, neural style transfer. So there are different options there. We can use some different applications that we can develop to make sense of our image data. But how does a machine actually see our data? And that's, let's say, the most important question we need to answer to try to understand how we can build deep learning neural networks. And here, the key is the numerical representation of images is needed. So for example, let's have a look at this slide here. How can we represent a grayscale image? So a grayscale image, you see here on the left side, can be stored, can be represented as a matrix, and where each cell represents one pixel of the image, and the cell value represents the gray level of the pixel. So for example, the black and white image, for example, in this case, we have a 5 by 5 image, so 5 pixels on one side, on the other. And you can see the black pixels are represented as a 0, whereas the white pixels have a value of 1, and the gray pixels have a value of 0.5. So again, each cell here represents 1 pixel of the image. But unfortunately, we don't usually work with, let's say, with grayscale images. We usually have tons of images that are in colors, and this is possible for a machine to work with and to represent. And normally, color images can be encoded, so the greens, the reds, and the blues can be encoded for each pixel using basically a tensor. So no longer a matrix, but rather a tensor where with basically one channel for each color. So for example, we could have a tensor where we have over the dimension of n times m pixels and k, which represent the number of channels. Usually we have 3 channels if we have color images. But besides, so now that we know that basically we need to have a matrix of values, right, of pixel values to represent images. So to let the machine understand and process images, what are the challenges that we have to face when we work with image data? And that's what we're trying to have a look at now. So imagine, for example, we want to perform a simple classification task. And so we have an image, the one you see on the left-hand side, where we have basically an X. So you can recognize the X because we have pixels with value 1 in there, right? So our goal here is to train a network to recognize that X. And one approach could be, if we use a simple feed-forward neural network, is to basically flatten flatten our input image. And by flatten, I mean by basically stacking each row of this matrix on top of each other, and then basically providing these values as input neurons for our feed-forward neural network, and then we can try to train our model to classify this the presence of an X or the absence of it. But there are a few problems with that. One of the major problems is, for example, is the existence. So we're going to create a lot of variables and weights. So just as an example, if the image has is a 224 by 224 pixels with 3 channels and 100 neurons in the next layer, we're going to end up with more than 150,000 inputs. And already in the first layer, we're going to have more than 15 million weights. So this becomes completely unmanageable, and it's likely to overfit, and it's extremely computationally expensive. So we need to have a better approach, a much more efficient approach. There is also, I have another problem that has nothing to do with efficiency, but rather with the loss of information. So because we need to flatten our input, so the network is not able to maintain special dependencies. So the first pixel of our matrix has the same or is, let's say, spatial agnostic to the network as it is the last pixel in our matrix. So basically, we lose that special dependencies, which are instead very important when we have, for example, objects in our images, right? And this is a problem that with a simple feed-forward neural network, we cannot solve easily. Beside that, there is another challenge which has to do with different variations of the image. So we want to have a network that is able to take into account, for example, that we have the picture of a statue, no matter what is the viewpoint. So we want to have a network that recognizes that there is a statue there, wherever the statue is looking, the look is downwards or is a little bit rotated, or whenever we have deformations in our pictures, in our images. For example, the picture here of a cat, or when we have different illumination conditions. So the network should still be able to recognize or to classify the picture as containing, as having some penguins or something like this. But also we want to have the network to be, let's say, robust against interclass variation. So if there are, for example, here in this case, different chairs or different shapes and styles, the networks should be able to label those pictures, those images still as a chair. So we need to have a network that, in that sense, is able to deal with such a variation. An idea could be, in that sense, to use, for example, a filter to check for different features. So, for example, we could have a filter. You see here the yellow one that checks for arm going from the lower right to the top left. Then we could have another filter that there is the one, for example, in blue here that check for crosses. And then another one that check for arms going from lower left to top right. So we could have basically introduce the idea of filters to check for different image features. And this seems already a much more interesting approach. But how can we apply a filter, and what is basically the impact? And that's exactly what we are trying to look at right now. So imagine applying a filter. So the goal of this, or having a filter in this case, would be, for example, if we have a high value. So applying a filter would mean that if we have a high value, it means that the feature that we are looking for is in the image patch. Whereas a low value would mean that the feature is not in the image patch. So let's have a look how this can be, actually what it means really when we have the picture you see here in the slide. So the idea is, in this case, to use a kernel or a matrix, which contains some values. And this matrix, this kernel, is placed on top of the image. And we slide this kernel across the image. And we basically do an element-wise multiplication of the pixel value and the value in the kernel and sum up all the values. Don't worry, we're gonna show you now an example. So imagine we have, you can see here the yellow filter or kernel, and you can see it's a matrix. It's a 3x3 matrix with some values in there. And basically we place that filter on top of the image, and we perform an element-wise multiplication. So we multiply 1 times 1, as you can see here in the calculation, and we sum then with the multiplication between -1 and -1, and so on. And so we continue until we basically cover the entire set of values, and we sum up those values, which give us a value of 9. And remember, whenever we have a high value, it means that the feature is in the image patch. What happens if we use the exact same filter also or canal for another part of the image patch? For example, the lower part. As you can see here, when we do exactly the same operation, in this case, we obtain a value 1. And this is telling us that in this case, the filter is not able to capture the image patch that we hoped for, because in fact, as you can see in our picture, we are trying to let's say capture with that filter the lower part of our X in the image. So it's not, so that filter is not, let's say, fit for the specific. So the values in the filter are not fit for the specific, for capturing that specific feature of the image. So, and therefore we have in fact a low value. And from a, let's say, from a mathematical perspective, what we are doing here, it's basically a cross correlation, but let's say in the deep learning community, what this operation is called a convolution. And we're going to talk about it in greater detail later on. But we don't need necessarily to have only one filter. We can have, in fact, multiple filters. And so, for example, again, we show a similar case. So we have an image within X. We multiply and sum the values coming from the element-wise multiplication, and we basically create an output metric. So we're gonna basically, as you can see now from the slide, we are gonna slide little by little our filter, and we have the multiplication and the sum, and we're gonna do this for the entire surface of the image. So we're gonna slide our filter slowly there. But how many filters do we need? Well, definitely not one. If you want to hope to have a good performance, so we can have in fact multiple filters. And whenever we combine the output of these filters, what we create is a feature map. Basically, is a representation of the most important characteristics extracted from the image. And so with this feature map, we can then work what we can extract for our classification task. So in this way, we can try to extract the most important feature from our images in an automatic way. Let's have a look how we can do in this sense, image classification. So defining, for example, which feature we want to extract from our images, we can assume to do it manually, but this requires a lot of domain knowledge, right? And but we also need to know how we can actually detect those features. So instead of doing this work manually, because it's a lot of work and it's let's say it's time consuming, and we also might not necessarily have the domain knowledge all the time, we can have a different approach. We can have, for example, a so-called convolutional neural network. Here again, we have the concept of the filters, and the values contained in the filters, so the value of our metrics, are being trained as part of the training of the network. And those values are able, because they are trained, the value contained there are trained, so they went through a process of training, they're going to automatically determine which feature to extract. And then the extracted feature can then be used by the network for the classification task. So in this case, for example, you would have an image of the cat. The network extracts automatically the most important feature out of the image for basically output the label cat. But how are convolutional neural network, so what they are and how they are structured. And that's exactly what we're going to look at this section. So a convolutional neural network is a neural network with at least one convolutional layer. And as I said, instead of basically having a filters that are handcrafted for different features, which of course can be done, but it's extremely time consuming. And we might also not have the domain knowledge, enough domain knowledge to know which value we should be placing those filters. Convolutional neural networks, what they do, they learn a hierarchy of feature using multiple convolutional layers and usually also many different filters. So for example, we usually start by extracting low-level features. That could be, for example, some edges, some dark spots, or nothing that it's still too informative. And we use those low-level features and additional convolutional layers to extract mid-level features, such as, for example, eyes, ears, nose, and so on. And again, we then use those mid-level features and additional convolutional layers and filters to extract finally high-level features. So, and in that case, we could, for example, obtain the facial structure. And again, as we already mentioned, all is based on the idea of a convolution, which is basically, again, sliding a filter, so a kernel, which contains weights that are being learned and trained during the training phase over the image, and the values multiplied and summed. We have, again, in this slide, we are going to have, again, we are going to reinforce again this concept of how a convolutional layer works. Again, as you can see here, we have our image. We multiply element-wise the value of the image and the value of the kernel. And then what is very important, we use an activation function. In this case, what often, let's say, is the Relu activation function. Remember, the Relu activation function is bounded between 0 and the high value itself, so the value itself. So for example, you can see here in the output of the Relu function, we have then only positive value and zeros. And let me stress once again, and that's one of the most important points of how convolutional layers work, is that basically this matrix of the kernel contains some weights, as you can see here, that are being learned during training. And this allows the automatic extractions of features out of our images without the manual handcrafting. And in a way, the process of learning those weights is similar to what happens in feed-forward neural networks. So that's, let's say, sort of a good analogy, I would say. But it's not just the convolutional layers that we need, but we also need, for example, to tweak a few hyperparameters. One of this, it's the stride. And the stride basically defines by how many pixels the kernel should shift across the image. So for example, you see a stride of 2 by 2. So we move always 2 pixels at a time. Or we can also have, for example, a stride of 1. So we shift the kernel by 1 pixel at a time. And this, what it does, it has consequences on our output size. So obviously, if we have a stride of 2 by 2, our output size will be much smaller. Another very important hyperparameter is the dilation rate. This basically tells us how many pixels we decide to skip in our filter, in our kernel. For example, in the first example, where we have a dilation rate of 1, we have a contiguous filter. So there's no pixels being, let's say, uncatched by the kernel. But in the second example, where we have a dilation rate of 2, you see that we basically skip, let's say, to consider 1 pixel from the input image, and therefore, so when we let's say tweak these values, again, also in this case, we have different output size, and that's important because we might want to this might be important according to our task. And as you probably have already noticed by now, whenever an image basically undergoes or is fed into convolutional layers, this image shrinks a little bit. So from the original input size, it becomes a little bit smaller. And it is important to notice that for example, information that is on the edges usually is less often catched, is less often used. And I will show you, for example, here in the slide, the animation. So you see, for example, that the pixel in the center of the image is captured much more often than the pixel on the edges. And therefore, basically, we are in a way missing out on some information. And how we can correct this a little bit. And this can be done by introducing the idea of padding, which is also another option that we can specify in our convolutional layer. And the idea of padding is that of adding an additional cells with 0 all around our images. And for that, we have two common settings. So we can have, for example, we can set it to valid, which means that we don't perform any padding, or we can have the option same, which means that basically zero padding is performed, so that basically the output dimension of the feature map is the same of the input dimension. So we maintain the same dimension of the input and output, and therefore we are able in this way to capture more edge information. How can we, let's say, implement a convolutional layer in KNIME Analytics platform? For that, we have the Keras convolutional layer. And this node, as you can see here, it's very simple to configure. So the most important part is, let's say, of course, is the insertion of an input tensor. This usually appears automatically when you connect the previous node. In this case, for example, we have images of 150 by 150 pixels with 3 channels. We then have to define, of course, the number of filters. So how many filters do we want? In this case, we decide to have a number of filters set to 32, a kernel size of 3 by 3, and a stride of 1. And we also have a dilation rate of 1, and we perform no padding. So basically, we are setting the things that we just saw in the previous slide, and as activation function, we use Relu. But important, and it's why I put, let's say, I put a yellow box around the input tensor. Later, so deeper in our convolutional network, you see that the input tensor will have again the information about the image size, so 74 pixels by 74 pixels. But the third value, in this case, corresponds to the number of filters used in the previous convolutional layer. And in this specific case, for example, in this new configuration, we have more filters, but we left the kernel size and stride and dilation rate unchanged. Another very important layer after the convolution is the pooling layer. The idea of the pooling layer is basically that of replacing an area of the image or the feature map with some summary statistics. Here, there's no parameters learned. There's no, let's say, there's no learning, but simply the performance of some summary statistics. So we can decide in which area this summary statistics should be performed, and we can have, for example, max pooling, where we basically out of an area of 2 by 2, we pick the highest value, or we could have average pooling. And in this case, we pick, obviously, we calculate the mean value, and we return that one. And why are pooling layer useful? These are normally very useful and between convolutional layers because basically they reduce computational complexity. And also they help extract the most essential features out of the image. So they reduce the complexity and in general improve the performance of the model. So it is a good. So that's basically the reason why they are there. And also in this case, we have a specific node for that in KNIME Analytics platform. And as you can see here, what we need to define is, of course, the pool size, so the area in which we're going to perform our pooling. In this case, we have a max pooling layer, and also the stride, right? So we decide by how many pixels we are going to shift each time we are basically computing some summary statistics. And so now that we have seen the convolutional layers, the pooling layers, and we know that there is always a Relu activation function in the convolutional layer, that's more or less how the structure of a convolutional neural network for, in this case, specifically for image classification looks like. So we have an image, that is our input image. We have a set, so we have a set of layers, of convolutional layers that are stacked on top of each other. And between them, we have pooling layers. The number of convolutional layers and pooling layers can vary, and and of course, the more convolutional layer we use, the more, let's say, the more refined our network is to extract image features, but also the computational cost increases. And once we have finally learned the features that we need, we can finally have in the last part, in the top part of the network, a fully connected feed-forward neural network for the classification. If we have multiple classes, so more than two, we would use a softmax, as you can see here, because in this case we are classifying vehicles. But if for a binary classification task, a sigmoid activation function at the end would do. And I would like to show you how you can perform image classification in KNIME. So we have, for example, a data set that we retrieve from Kaggle, where we have dogs and cats. And so basically the idea here is very simple. We have a binary classification task. We want to assign a label cat or dog whenever we have a cat or dog in our image. So how can we do this in KNIME Analytics platform? So here how we can build a simple convolutional neural network for image classification. So in the lower part of our workflow, we ingest the data. So we read the data, we normalize our images. So we do a little bit of pre-processing. We normalize our images. We resize them to the size 150 pixels by 150 pixels. And we finally use the partitioning node to create a test set and a training set. So mind or consider that this is a label. We always need a labeled data set if we are in a classification in supervised learning, as is the case. And the upper part of the workflow, on the other hand, we are defining the network structure. So as you can see, we have a Keras input layer where we are ingesting basically the size, the shape of our images. And again, we have a 150 by 150 pixels and 3 channels because we are working with images that have color. And then we stack a series of convolutional layers that are alternating max pooling layers. And as you can see from the annotations, we have in the first convolutional layer 32 filters, whereas in the second convolutional layer we have 64 and so on. So we can, let's say, play with these parameters and obviously adjust them to the task that we have at hand. And in the lower part, where we have the flattened layers until the last Keras density layers, there we are defining a fully connected feed-forward neural network. And as you can see, then we have a Keras network learner that is basically used to train the model over a defined number of epochs. And whenever the model or the network has been trained, we can apply the learned model to new unseen data to the test set, thanks to the Keras network executor. And finally, we determine whenever the value is above or equal 0.5 is going to be labeled as a cat. Whenever it's below 0.5, it's going to be labeled as a dog. And as you can see here in the metrics, we have an accuracy with this model of 74%. So it's okay, but still there is definitely some room for improvement. And maybe some of you may wonder, how do we? What are the best? Let's say, setting option for the filter, kernel size, etc. So the answer to this, it's not easy. Sometimes it is a good idea to look at some popular convolutional neural networks and see how in the research or in the literature this is being done. Or we can, for example, play with some parameter optimization. So we can optimize those parameters. This, of course, may take a long time, may be computationally expensive, but it will let's say, provide us with the most suitable kernel size or number of filters for our task. So once we have finally trained our model and we are satisfied with the with the performance of the model, we can deploy our convolutional neural network. So this is the phase of deployment. So as you can see in the first part, we have again the same preprocessing that we did during training. So we normalize our images, we basically resize it to 150 by 150 pixels. And then we use the Keras network reader to basically ingest the trained model. And again, we use the Keras network executor to apply the trained model to new unseen data. So here, because we don't have labels to our pictures, we need to find a different way to evaluate the performance of our model. And therefore, we can create a sort of we can have a visual inspection of the model performance, and we can create a basic composite view in KNIME, and that's exactly how it looks like. So how do styles being given the right prediction? Are those images being given a dog or a cat prediction? And if you just look at the label, the predictions, you would see that basically the model is pretty robust, because if there are out of 10 images that we have here, there are basically 3 mistakes, which means that basically we have pretty much 70% accuracy in our prediction, which is exactly what we obtain during training. But as I said, is there a way we can improve the performance of our model without, let's say, incurring the computational cost of training a convolutional neural network from scratch? And the answer is yes. And this is what transfer learning is about. So in standard learning, we have a data set for the task A, and basically we model, we build a model for task A. Or then we have a new data set, new data for task B, and we create a new model for task B. So this is obviously requires the creation and the training of a new model each time we change the task. But in transfer learning, what we want to do is we want to capitalize on what the model has been learned for task A and apply that knowledge to the extent that is possible and makes sense for a new task, for example, task B. So this knowledge transfer is extremely useful because it helps us reduce training cost. It helps us also capitalize on the work of others, and therefore we have a much, let's say, a much faster procedure. So, in which case, for example, in which let's say, what would be, for example, a good example for transfer learning in a specific case of image classification, or why will we need it, in which extent? So, for example, imagine we could use a popular architecture, which is VGG16. There is a convolutional neural network that has been already pre-trained, and we want to use it to solve the cats and dog classification task. And there are many ways in which we can use, in which a trained network can be used. For example, we can decide to reuse only the network structure, but we can also, and this is probably what happens most of the time, we use not only the network structure, but also the weights that have been learned. And we can, for example, decide to use only some layers, all the layers, so they basically apply the model straight away, or basically add some new layers on top of of the models, and then basically do a new, just train those top layers. And again, why is this helpful? Because usually to train very, let's say, effective and accurate models, you need thousands or millions of images. In the example that I showed you before, we just worked with about 4,000 images, and we've still already reached 74% accuracy, which is not bad. But to have a better performance, or considerably better performance, we need thousands or millions of images. And VGG16 was trained, in fact, on more than 1 million images from the ImageNet data set. So, and just to give an idea of how this VGG16 looks like. So again, you see here from the legend that you have in the lower right lower part, we basically have an input image and then a stack of convolutional layers that have a Relu activation function, followed by max pooling layer, and again, a new convolutional layer. And so this is basically being stacked one after the other until in the last part, we have, of course, again, a fully connected feed-forward neural network. And with in this case, since VGG16 is trained to classify 1,000 different classes, then they use a softmax, but we can, let's say, we don't need it if we have a binary classification problem. And so how can we, let's say, decompose and decide what to use? So here we have, again, the same structure. So convolutional layers and pooling layers. And then the last part is the feed-forward neural network. And so we can decide to use all the layers until the last pooling layer, and without basically training, and just replace and retrain the feed-forward, the fully connected feed-forward neural network for the classification part. So we basically capitalize on what has been learned before by the network and apply it to our dog and cats data. And how can we do that in KNIME Analytic platform? And by the way, you always have the links to the workflow on the KNIME Hub. So as you can see, the lower part is still the same preprocessing, but in the upper part, we have a deep learning Python network creator. And here we read the pre-trained VGG16 convolutional neural network with a few, let's say, line of code. And then we use the Keras freeze layer, which basically only trained 3 new layers. So all the previous layers, as you can see here in the image, so the non-trainable layers on the right-hand side are all the convolutional layers that were trained during, that were trained before and that are made available in the deep learning Python network creator node. And we just decide to train the dense, the dropout, and another dense layer. So that basically the last 3 new layers. And by doing this procedure, we obtain a much better accuracy of 91%. So it is less expensive for us to create a network, and it also achieves a much better accuracy. But we can also have an improved version of, let's say, of this transfer learning, and which is option 2, which is based again on the idea of using pre-trained model. Again, in this case is VGG16, but in this time we apply the model to basically to nuancing data, for example, to read and preprocess images. So we have that a meta node where we read and we encode our images, and we apply the model thanks to the Keras network executor. And after that point, we just train the upper part of the workflow, so where we define the fully connected feed-forward neural network. And this part, so in this, let's say this second option, only the training part takes about 90 seconds. So by that, I mean the execution of the Keras network learner node. It takes only about 90 seconds because we avoid the image to be, let's say, moved across the entire convolutional layers during the training process. So this is it's a much faster process. And again, also in this case, we use, as you probably already understood, the VGG16 for the feature extraction. And with that, we almost reached the end of our webinar. So what's next, let's say? If you have, so you will find all the material, the recording, and the links to the workflow. If you go on the KNIME forum, there is a section for events, and there you can see the webinar that we are having today. And there we will be posting all the material that we've been going through today, plus the links to the recording and to the slides. And the last few words, if you want to keep update and to, let's say, read what the community has to share, I invite you to visit our publication on Medium, which is low code for advanced data science. These basically contain, so this publication contains story submitted and published by the community. from data science theory to successful data science stories. There's a little bit of everything. And you're, of course, more than welcome to contribute with your own story. But if you want to learn more about codeless deep learning with KNIME, I really recommend this book. This was written by Rosaria Sillipo, which is head of evangelism at KNIME, and Catherine Melcher, which is also a KNIMer at KNIME data scientist. And this is, I'll leave you the link there so you can have more information. And you can also have a look at that link at the first chapter, which is for free. And with that, I would like to thank you for your attention. And now we have a time for questions, so feel free to speak up, and I'm happy to try answer your questions. So maybe I will ask Emilio, is there any question from the audience?
Yeah, so there were a couple of questions.
Yeah.
Actually, like for example, I've already answered, but maybe it's worth repeating. How to decide which kind of filter we have to use, and you have already explained that actually we don't have to decide the filters, and that's the cool part of CNN. And also another question was how do we choose the number of filters for the convolution, and that was also covered.
Yeah, we can repeat that. Maybe it's good repeating that. Let me go back to the slide where we had that. Oops. All right, so here more or less. Okay, so so choosing the size of so choosing the number of filters or the kernel size. So again, the filter size. It's not a trivial task, and these questions are definitely interesting. And the truth is, there's not like a sort of a handbook of values that you can plug in, and that's it. It depends on the kind of images that you have. It also may depend a lot on the kind of pre-processing that you did in the beginning. Maybe you need to reconsider the pre-processing before to improve the performance of your model at the end. But deciding the number of filters or the size, it's to a certain extent a little bit of trial and error, unless you have, as I was pointing out here, you can have a look maybe at some popular convolutional neural network that will be built for a specific domain of images in the literature. So, for example, imagine that you want to classify different art styles, and therefore you will probably have to look at similar convolutional neural network that were engaged in similar tasks, because this may give you an idea of how those models in the literature were trained, what was the right amount of, or in that case, the right amount of filters, or filter size, but also what pre-processing maybe was needed. Or for example, sometimes you also have the problem of not having enough images. So we might need to engage in a process of image augmentation, right? So to create new images, maybe just by rotating those images, by introducing some noise, by synthetically generate some new ones. So there are several options, but specific to the number of filters and kernel size, this is something that you can do a little bit of trial and error, or for example, you can do a parameter optimization. So we have parameter optimization nodes in KNIME Analytics platform. You can plug those in and try, and basically those nodes will try to optimize those numbers for you. How and when do you optimize this, and which strategy? This depends on you. We have different strategies, from the brute force, which will try every single value in a scale from, I don't know, from 20 to 30, or Bayesian optimization. We have many different ones that you can select. And the problem with that is usually that is, let's say, it's computationally expensive to run parameter optimization. And therefore it needs to be, it needs to be used knowing that which computational power your machine has. So it is definitely a possibility, and most likely is one of the best possibility you have there, especially if you don't have any other reference in the literature, but you need to be aware that that can be computationally expensive. Another option could be maybe to change the network structure, right? If you change a little bit the network architecture, maybe adding more convolutional layers, sometimes this can help, or using maybe instead of max pooling, like in this case, maybe average pooling. So again, this depends a little bit on the task at hand. Yeah.
Yep. Thank you, Roberto. There are a couple of more questions, actually. Yeah. One is from Lisa and asking, that we can answer quickly, about where to find the workflows. And we can say that on the slides, there are the links to the workflow on the KNIME Hub. So you're going to have everything there. So all the material we share with you. And then there is another question by Daniel, asking, what would you use for an NLP task versus a picture task? So I don't know if Daniel wants to maybe give more a specific example. Or...
Yeah, I can maybe try to provide an answer, and then Daniel, you can tell me if this is the direction you were expecting the answer to go to. So usually, if you want to use deep learning, let's say for an NLP task, so remember that we are working with, so NLP usually has to do with text. So and information in text is sequentially presented to the model, right? So the order in which the words appear is extremely important. Similar important in terms of sequence is also for time series analysis. So there we have time that is important, and this variable needs to be included into the model. So whenever we work with an application in NLP, and because we need to, let's say, we need to introduce this element, this order of elements, but also try to capture context information, right? Imagine, for example, we want to do some sentiment analysis. So in that sense, a much better fit, or at least in the literature, it's shown to be a much better fit. It's, for example, using recurrent neural network with LSTM units. Because those networks, I mean, the way they are constructed and the way they are built, they are able to model and to map dependencies in text in a much more efficient way. So you are able, so those networks are able to, let's say, map the fact that the adjective was positive and therefore is affecting the meaning of the entire sentence. And still, nowadays there are even better models than that. If you have ever heard of BERT, which is a transformer-based architecture that was created in 2018 by Google, they have a completely different structure. So they abandon the recurrent neural network with LSTM unit to have a different approach. And those are actually what is being, so the transformer-based architecture are what is being currently used for NLP tasks, from question answering to sentiment analysis to topic modeling and so on. So it's not common to use convolutional neural network for that, but it's rather much more common to use convolutional neural network for image analysis, and such as the case that I show you in this webinar. Now, Daniel, does that answer your question? You can write down also if you prefer.
Yeah, Daniel said thank you. Right. And there is another question asking, and this is worth repeating, if KNIME Analytics platform is a paid application.
Okay, that's a very good question, and thank you for asking that. So let's say level up. So KNIME Analytics platform is an open source and free software for data analysis, for data science. What does it mean that it's open source and free? It's free because you can just go to knime.com, to our website, and download the software, the platform, straight away. So, and you can start straight away creating your data science solutions. You have all the capabilities of extensions, community extensions, integration that you can install from our KNIME hub. So this is free in that sense. You can just download it for free and start using it right away. And it's open source because the code that is KNIME is being developed on is made available for everybody to have a look at and to use it in a way. So, and this is, I think, stored somewhere on GitHub. And basically, you can just go to our website, go to the download button, click in there, and you can start using it right away. And also maybe that's obvious by now after the webinar, but another important characteristic of KNIME Analytics platform is the fact that it is based on visual programming, right? So in all the application, all the workflow that I show you today, there is almost no code. So we use rather this visual programming, which is basically based on the idea of drag and dropping some elements, the nodes, onto your workbench, connecting those nodes in a sequential way, and let those nodes perform some actions on your data. We only use Python, a few Python lines here when I was talking about transfer learning, because, for example, in the deep learning Python network creator, there we are using a few lines of code in Python to import, to read the pre-trained, to basically download the pre-trained VGG16 convolutional neural network. But beside that, everything is done completely codeless, in a completely codeless fashion. And it's something that it's important to stress. Codeless doesn't mean mathless or theoryless, right? So the fact that you don't have to program or you don't have to code doesn't, let's say, remove the theoretical complexity or the theoretical knowledge that you need to have to build meaningful data science applications. So we just have a user to have all their work, to create their work in a perfectly integrated environment where they don't have to worry about installing dependencies or going crazy with the command line or hundreds of different complexities that are usually part of the experience of those that, let's say, use coding, traditional coding to develop their solutions. Does that answer your question? I don't know who asked that. I hope it does. Or otherwise, just ask more.
Yeah, and also there are some people with the raised hands, but I don't know if they can speak up, or if not, please feel free to write down on the Q&A and we can read your question.
Yeah.
There's a new question. Do you have any experience using this type of workflow for image from hospital, like MRI image or scan image from radiography?
I think we do have something let's say, in the healthcare sector, but that was, I think, for cancer recognition. So the classification of whether cells have cancer or not. I'm not sure if that is exactly what, I'm not an expert in, let's say, in the life science domain. So so I tend to avoid working with those data, with that data, because of course, sometimes the data, so the domain knowledge is important to make sure that you are identifying, or you can check what the model is identified as cancer or no cancer. So I know there is some solution developed in that sense, but I am not sure if there is anything more specific. Let's say the best way to find out is to go to the KNIME hub, which is our repository for nodes, workflow, extensions, for everything. It's a huge repository of resources, and you can simply, there's a search bar there, and you can simply type something like image classification, deep learning, and then you would have their whole list of workflows that are available for image classification. So maybe that is, and I think you will find there the one about identifying cells that have cancer or not. So maybe you can build that on top of that afterwards. Yeah. Is there any more question?
Not that I can see at the moment.
All right. Let's see, maybe let's give another minute, and then it's 6 p.m. So maybe 1 more minute if somebody is still typing.
I'm having some problem with Zoom, so I don't know if there are more questions. I actually don't know if I can see the updated ones. So if you can check, that would be nice.
Let's see if I can find it.
Sorry for that.
I think I don't see any right now. So yeah. Anyway, maybe there's more question. I invite you to maybe to unmute yourself because I cannot see any either. But maybe it's also me that I don't see all the question correctly. So if there is any more question, last minute question, please feel free to unmute yourself and speak up. Otherwise, I would wrap it up the session. And thank you, all of you, for attending this webinar. I hope you had a chance to learn a few new things. As I said, the recordings and the material will be made available on the KNIME forum. So check the thread about this webinar there. And then we also prepare, I will post it tomorrow, a small exercise where I ask you to, going back here, to improve the performance of a simple convolutional neural network by just either doing some parameter optimization or by changing the network architecture, or by doing both. So this is really up to you. Show me how you can improve this performance without using transfer learning. That's important, and also because this hopefully give you some good practice, some time to practice, and to get your hands dirty with something practical. And yeah, so with that, I would like to thank everybody and see you soon, I guess.